Hello, today me and my partner are going to present Lorentz force law and its role in electromagnetic energy. So this is our assignment title. So before we begin with our slide, I'm going to introduce myself. My name is Azri. By my score, my market number is B082110440. My other partner is physical SAMIDAS is B082110509. So this photo, this scientist is Henry Lawrence, the scientist is credited with creating the Lorentz force law, which is fundamental to our knowledge of how the charged particle interact with an electromagnetic field. What is Lorentz force? Lorentz force is an electromagnetic force experienced by a charged particle in an electric field and magnetic field. If the electric field is zero and will assume it here, then Lorentz force is a purely magnetic force acting on charge as it moves through a magnetic field. Well, if no moving charge or no magnetic field, then there is no Lorentz force. So F equal force, Q equal charge, E is the field, V is the velocity, B equal magnetic field, which F equal Q bracket E plus V minus B. So this force is a thing for the electric field is expressed as QE, while the force for magnetic field is given by second term QV times V. This magnetic field force is perpendicular to both the velocity vector and the magnetic field direction. So what is the relationship between magnetic field and electrical charge? The lowest force is the force on a charged particle due to electric magnetic field. A charged particle in an electric field will always feel a force due to the field of magnetic F equal to E. A charged particle in a magnetic field will only feel a force due to the magnetic field if it's moving with a component of its velocity perpendicular to the field. If it is moved parallel to the magnetic field, it experiences no force. These two forces are often studied separately, but the sum of these two forces gives the force that we call the Lorentz force. So this is an example of the relationship between magnetic field and electrical charge of Lorentz force law. So this is a charged particle moving to a magnetic field. We can use the expression F equal QVB sin theta. So because a charged moving particle moving to a magnetic field of strength V with speed V will feel a Lorentz force with a magnetic field of where theta is the angle between velocity of the particle in a magnetic field, which is field lying from north to south, and Q is the charged particle. This force acts at a right angle to both the magnetic field and the velocity of particle. That's for me. The partner is going to continue the slide.
Hello everyone, I'm Jessica here. Would like to present from this current carrying wire in magnetic field. A current carrying wire in magnetic field will feel Lorentz force in direction given by Fleming's left hand rule with a magnitude of, okay, here you can see the formula, F equals to ILB sin theta, where L is length of the wire in the magnetic field, I is the current flowing through the wire, and theta is the angle between the wire and the magnetic field. So this is the Fleming left hand rule. And next we can see the concept here. So here I will explain how it works. The Lorentz law is a phenomenon observed in a current composed negative charge particles or electrons in motion through a wire. So we can see electrons, the yellow particles shown here is electrons moving from negative to positive. Next we can see here electric current flows from the positive to negative terminal, which red particles moving here is from positive to negative. So now it's not switched on, so it remains stationary, which it don't produce any magnetic field. Next, when it is in motion, it will generate a small magnetic field in its vicinity, which you can see here. When it's working, it will generate small magnetic field, and you can see the arrow in circle, green arrow in circle, which is magnetic field. Next, when we reverse the polarity of the battery, positive and negative, we reverse, we can still see the magnetic field here. This is the output. Next, we are using the horseshoe magnets in order to see what it will effect, because we are using this horseshoe magnet, for it is similar with the magnetic field. Either it repel or attracts each other, that from generating by the current. So we insert the horseshoe magnet into this setup just now. Here you can see we have set the circuit, like the wire is set here as perpendicular, which it will swing either in different direction, left or right, when there is a magnetic field generates. So here you can see the flow of electric current. This is what happens when we switch on. The magnetic field of the horseshoe is in the wire is swinging on the right direction, which is due to the current's motion. Next. So now we are reversing the polarity. Again, we are reversing the battery, and we will see what it will happen for in this diagram. We can see the direction again swings in left direction. The wire direction is swinging on the left, and we can see the magnetic field. Next. Next, we can see finally it's reversing the horseshoe magnet. Just now we were seeing the sort, and sort was above and not was below. Now we reverse the polarity, the horseshoe magnet's direction, which not at above and the south at below. And we can see still it affects the direction of the swing, which it turns to the right, and it produces magnetic field as well. Next. Next, I want to talk about the applications of Lorentz law, which is the main application. We can see hydrophone here. Hydrophone is about, okay, in Lorentz law, for this application, it is used in medical industry from an instrument known as hydrophone. The ability of the Lorentz force to link a mechanical displacement to electric current presents a strong interest for medical acoustic. So here we can see hydrophonic for a quantitative evaluation for medical ultrasonic probe. Next. Last but not least, conclusion. The application of the Lorentz force in slide plays a pivotal role in understanding the interact between charged particles and magnetic field, as we've seen in the previous slides, how it works. As elucidated in the presentation, Lorentz force is resultant force experienced by a charged particle moving through a magnetic field. This force perpendicular to both the velocity of the particle and the magnetic field causes the charged particle to follow a curved trajectory known as the Lorentz force trajectory. This phenomenon finds practical application in various fields such as physics and engineering, including the design of the particle accelerator and magnetic confinement devices. By comprehending and manipulating the Lorentz force in slide, researchers and engineers can harness its principle to develop innovative technologies with implications for scientific research and technology advancement. Thank you, and that's all from us.